Hello, everyone. Sorry for the delay as it had temporary audio issues. I believe we have everything corrected now. Our subject matter expert for today's webinar is Chris Urbanski. He has his PEng and PE in Texas and Nevada. He's a lead structural engineer with Landmark Engineering. Chris has more than 20 years experience delivering civil and structural engineering solutions for energy, petrochemical, pipeline, and infrastructure across Canada and the US. Been responsible for projects from FEED through construction, total installed costs of up to $300 million. His expertise spans facilities, tank terminals, foundations, modular structures, pipe racks, and modular compliance. Led projects from clients including TC Energy, Wolf Midstream, Orica, and Imperial Oil. Please join us in welcoming Chris Urbanski. If you have any questions during the presentation, you can use the hand icon or type it in the chat. We'll also leave time at the end for Q&A. If you have any specific questions, you can also email Chris or myself. And with that, Chris, I'll turn it over to you.
Hey. Hi, everyone. I'm Chris Urbanski. As Mitch pointed out, everyone hear me okay? So please speak up if not. And I will get started here. All right, hello, everyone. So thanks for the introduction, Mitch. I'm going to chat with you today about civil structural engineering, kind of what our group does, what we do generally, and kind of how we work with other groups within our own organization and outside of it to get the inputs we need, as well as to provide the information to those groups that they need to complete a full integrated design for petrochemical, upstream, midstream, other types of industrial facilities. So title here is Structures, Foundations, and Pipe Stress, Getting the Interfaces Right. Bit of a contents here. I want to chat about pipe stress and structural, kind of who does what and how we work together. It's a very important, in my mind, interface for our industry here. Make sure that we're both talking to each other and that we come up with an efficient design together. So, and then after that, just kind of talk about generally what we do, the inputs, calculations, and deliverables. Prelim info we provide, kind of the inputs we need to do our design, which includes pipe stress, geotechnical, survey, piping design, and vendor information for buildings and equipment. And then analysis we complete, which is engineering calculations, for structures, foundations, and for strength and serviceability, and lifting and transport. So I guess to really bring it back or start it off, I mean, the main thing we're doing is making sure things don't fall down. Have some examples of some failures here. In the left, punching shear failure. Unfortunately, a relatively common type of failure for a building, but we designed for it. Make sure that there's sufficient strength at the columns, so this can't happen. This is a picture here of the floor above punching through at the columns and falling to the floor below. We also have a electrical tower that the windstorm here and the individual members buckled and then collapsed and the whole tower went down. Bending failure of this overloaded deck, maybe a connection failure too. Other type of failure where we're just straight compression of a short concrete column. It's just being crushed under its own weight. And then the other thing we often deal with is steel beams running long spans as the bridge girder that's torsionally buckled and failed. I'm sure we're bracing for that and designing for that as well. So to give an overview, I kind of give this internally and externally of kind of what we do and what we don't do. So for our structural group, we're working on concrete and structural design, pipe support structures, foundation design, and then we do get into civil design for site grading and backfill and drainage for roadways and driving areas, tank bases, and retention ponds and that sort of thing. But what we don't do is determine where the pipe supports are required. We don't design pipe supports themselves. Those should be familiar, like insulated pipe would have a pipe shoe so that it can sit on the pipe or on the structure still and leave space for the insulation and straps. At certain points, the pipe stress group is going to provide a guide or anchor. A guide would restrain the pipe laterally on the support. Anchors will restrain it axially on the support. And then in specialized situations, we'll have trunnion supports where a piece of pipe is welded onto a pipe, and then we support that trunnion of the structure. But we rely on our pipe support group to design those components. So if it's attached to pipe, it's a purview pipe stress. And then the other thing that kind of gets beyond, or we're working with other teams, is if it's above ambient temperature and pressure. We're getting out of the structural codes and getting more into ASME codes for boiler and vessel design, and then overall, pipe stress analysis by others. But I do want to just kind of talk about the interface between them. I think it's important for any mechanical engineers in the crowd, or even other structural engineers or other disciplines, just to understand kind of how we're working together and how we can build the most efficient design. So engineering, reviewing, and stamping isometric piping drawings. We have an example here. They're responsible for ensuring the pipe spans are reasonable to not overstress the pipe, so the distance between supports. Responsible for what support types, as I described, whether you need guides, anchors, pipe shoes. And then our civil structural group, is responsible for the design of the structure and foundations at the support points. So generally we have mechanical engineers working on the piping design with our piping designers, and then stress engineers going through and informing where these supports should go. And we kind of call off some standard support types, or a mechanical engineer would, and this would be what be resting on our structure. On the left, we have kind of a standard clamp shoe that we generally use. And on the right would be an example of a guide for that shoe, where we have pieces of steel on either side, restraining that pipe shoe from being able to move laterally. And then we need to design the structure underneath for that loading. So just to kind of look at it from a facility sort of model point of view, 3D model of a well pad facility here. Got piping running from the wellheads to various equipment packages and tanks. So the support spacing is not civil scope. We rely on kind of the designers using span tables to set that initially. Make sure we're not beyond what a water-filled pipe can span, and then get stress involved to check it for the actual piping conditions. Again, support type, that's coming from them, and then our scope is everything below that. So we're designing structural steel supports, we're designing the piles, and we're designing the piles or other type of foundations, whatever it may be, for the buildings, tanks, and equipment packages, as well as the pipe supports. So just kind of back to how we interface together. I mean, sometimes things move quick, doing small installs. May not, either the piping small or not high enough temperature that the mechanical engineer may make the call that in-depth stress analysis isn't required, or the client may not require it for that size. We still may do it depending on the complexity of the project, but if we do go down that road, essentially the piping engineer is accepting responsibility for that on their own, either engaging stress or going through it on their end if they have the experience and the comfort level to do it. And then we would just be designing for the loading based on pipe span tables, kind of worst case loading, based on split standard rules of thumb and empirical rules. And we can do it. It'll just end up conservative. So it's something we do for smaller stuff, but as soon as we get into larger stuff, we really want to work with a stress engineer so that we can work with them to provide support information, stiffnesses. They can work with us to provide loading, and we can come up with an efficient design. So what the issues and failures we're trying to prevent on the piping side: flange leakage due to inadequate support, piping sagging due to inadequate support, or pipe failure due to inadequate support. And then on our side, civil structural, we're looking at structural failure, so the actual supports not failing due to overload, the foundations behaving adequately. So we want to make sure the foundations are not settling too much or jacking out of the ground due to frost. Get into that a little more later. And then we need to make sure the structural deflection isn't too high to support the loads in the first place. So that's kind of the rundown of kind of how we work with stress specifically. And this is more of a general sort of chart on how we work. So kind of go through this. If there's any questions, please interrupt, and Mitch can let me know. I can address. So we start with what we need for the preliminary info. We can do some preliminary structural analysis to provide support stiffnesses that the pipe stress team can use in their analysis. We will help provide scopes of work for survey and geotechnical, and those kind of, and then we get into our input. So the preliminary stuff, we'll go through. This is an example of a skidded structure. There's piping on all these supports, but this is just the structure itself. Every point you see with the red, green, and blue arrow is where a pipe will be supported. So we'll go through and model the structure and provide a stiffness at each support. If anyone remembers Hooke's law, it's just stiffness values in kilonewtons per millimeter. So how much force you push on it, it'll take to deflect it a millimeter. And then pipe stress team can use that to actually see how much these supports are restraining the piping, or if they're moving with the piping. We may need to do both. I mean, they may need a stiffer support to restrain the piping so it's not overloading the nozzles that it's connecting to. But if they assume that every support is infinitely stiff, for one, that may not be the case. So that may be unconservative, that we're assuming rigid supports might be restraining the pipe when it's actually not, and those loads are going into the connecting flanges or nozzles. And we end up designing the structure for much higher loads than actually required. So if we can do this for them, they can start with this, and then we have an iterative process where we're going back and forth and making sure that the support stiffness meets their requirements, and that the support strength is sufficient for any loading imposed. And then we'll provide scopes of work to get either both survey and geotechnical involved, especially for larger projects. So we can get all the information we need. So I won't read through these completely, but just a couple examples of what we will ask for. So survey scope of work, we're going to outline exactly what we are looking for as far as what we need them to shoot. So we're going to ask for a grid spacing, going to identify any kind of low points, high points, any survey benchmarks on site so we can tie it back into real coordinates. And then as well, work with the mechanical team for tie-in points, flanges, where we're actually tying piping in, existing equipment we're tying into, and have all that surveyed so we know exactly where in space it is and can use that for our design and model. And then geotechnical, we have some in-house capability, but generally we're reaching out to third parties to do a full investigation for larger projects. So we'll actually help put a scope of work together for that. We'll lean on the geotechnical engineer because they're the experts there as far as how many boreholes and where, tell them what we want to build, and work with them to determine those locations and how many and how deep based on their experience in the area, and then let them know everything we need to know, what kind of foundation types we'd like to use, if they can confirm it's appropriate, provide us the values, provide us the seismic site class for the site, and any dynamic info for designing machine or equipment foundations. We need to look at the interaction with the soil and the equipment. And that covers our preliminary stuff that we do. And then we're essentially, that informs this inputs row, which is what we need to do the rest of our design. So with pipe stress analysis, report results, site location and site survey, site geotechnical report, equipment and package specifications from the vendors. That will kind of left electrical out here a little bit, but that will also encompass our electrical group. So any transformers, electrical equipment, cable tray, panels, we'll get the specifications for that for our structural design. And then the piping layout, size, schedule, and C class, the full piping design. So to go through those, this example of once we've kind of done the preliminary back and forth where we provided some stiffnesses and started out with our designer with some support locations, especially for brownfield, we would take that and as a start and put supports where we kind of know we can support it on existing structure, and then send it to the stress engineer. And this is autopipe model, where they went through and supported the pipe or put support points in the model where needed, and then provided the loading at every single support with as applicable. For vertical, lateral, and axial loading under each cold operating, hot operating, and any other load cases that may be applicable. So we'll have that as inputs for our structural design. Same with survey. We'll get a nice, hopefully nice CAD drawing that looks like this, that outlines sort of any individual spots, culverts, ditches, drops, hills, existing soil piles, existing roadways, existing legal boundaries. And then we'll use this to develop the civil design, lay out the site. Geotechnical report, same idea. This is kind of an example of what we'll get back from a geotechnical engineer. This entire report. On the left, borehole data showing what the soil conditions are at different depths. They'll drill a hole and take core samples all the way down. Pretty expected here. We see topsoil at the top and then get into some stiff native soils and maybe bottom out on rock, depending where we are in the world. And they can give us design info we use, so dynamic info if required for machine foundations, and then a pile. This is just for static driven steel pile design, which is very common for us to use as a foundation. It's efficient and can be installed in remote areas without large crews and rolling mixed concrete. Equipment package specifications, fairly straightforward, but we do a lot of vendor supplied buildings, equipment packages, tanks, that sort of thing. So we're looking for weights, layouts, if they've designed the framing, where they need it to be supported. And we'll design the foundations for it. And then I guess the big one is the piping design and model. So once we kind of piping, we'll go and lay out the piping designers will lay out the piping. We've got an example here, but where we're using a scan model of a brownfield site. So everything black or kind of grayish is the point cloud from a 3D scan. And then we're running new piping through here, connecting to a filter system. This is a water filtration project, connecting to a filtration system on the inside of the building. And then running piping to it. So then we're designing structure, best here, but a full struct, the white structural framing in here, supported on an existing concrete pad to support the piping. And then out in here where we've reviewed the existing rack and added steel where needed to support new piping running through there. So yeah, that covers the inputs. Say if you have any questions, guys, feel free to throw it in the chat and Mitch can interrupt me. That covers our inputs and what we need. And then next we're moving into what we do, which is the engineering calculations. So we have a list. We're looking at different loading on the structure. So simpler, maybe simpler, but like for buildings, bridges, kind of non-industrial stuff, the most important, and for any kind of buildings we do or platforms we do, the most important load combinations or loading and combinations are the snow load on the roof or the platforms, live and dead load. So dead load encompassing any equipment, the weight of the structure and building itself, and then live load would be anything that could be moved onto it. So personnel, vehicles, cart loaded with equipment, anything that's kind of off, on and off, or can be removed and added. So we'll just be designing for a maximum expected load based on the building code. And then same with wind and seismic. We're reviewing the lateral loading on the building due to earthquake loading and wind loading. Depending where you are in the world, one or the other might govern. We have to have a look at both. And the type of structure as well. It can depend. And then the real important one for us, for industrial stuff, pretty much everything we do, whether it be upstream, midstream, petrochemical, is going to involve piping. And it's likely going to involve piping that has quite a temperature differential depending on whether it's operating or cold. So we're designing our structures for that expansion and contraction due to temperature. We also need to look at our structures generally for temperature. If we have a really long pipe rack, a really long bridge, the actual ambient temperature can be enough for the expansion and contraction to become an issue. If you see expansion joints in buildings or bridges, you kind of see a rubber or polymer sort of joint. That's so the structure can actually expand and contract there without that expansion or contraction causing enough forces to crack or overload the structure. So we do look at both, but for us, the main one is the piping itself and the temperature from that. And that's again where we're working with the pipe stress beam to make sure all those loads are known. And then another very kind of important one we're always looking at, we do a lot of modular structures. So we're having a look at what how the structures or equipment or modules behave under lifting and transportation. So if we're designing a full package, we'll design it with lifting lugs. If we can, 4-point lift is ideal. That's 1 crane or 3 spreader bars. Generally, like we have on the left here, when you're lifting a package like this, this one's an 8-point lift that we have on the left here, but usually the lifting lugs will be designed so those cables have to be approximately vertical, especially if you have a building in the way. You'll have side-mounted lifting lugs like we can see here. Maybe removable, maybe not, depending on the requirements of the project or the maximum shipping width. And those are generally designed for vertical lift only. So you'll see a lift like this where we're telling them that it can only be lifted vertical, so spreader bars need to be used. So spreader bars across the building and then spreader bars across the length between the lifting lugs. And then in this case, if you're trying to do an 8-point lift with 1 crane, you'll have a last spreader bar between the 2 arrangements, or it wouldn't be too uncommon to see this being lifted with 2 cranes, 1 from each point. Or if it's a smaller package, ideally we just have it so we build the skid so it's stiff enough and strong enough. It can be lifted from 4 lifting points. Kind of this whole assembly ends at the point below the yellow spreader bar here. So that becomes important. I mean, we're balancing strength of the skid for a one-time lift with its strength sitting on likely more piles or more foundation points on site. So yeah, it really depends on the requirements of the project, the size of the skid, but if we can, we'll make it stiff and strong enough for a 4-point lift. That's the easiest to get it on site and get it installed quickly. You know, if cost of steel or the module's quite large, we add more lifting lugs. That means it's supported at more points while it's being lifted. Gives the option to use a lighter structure. And then we also have to look at transportation. Just while this is sitting on a truck or a train, it needs to get to site in the first place. So we'd have to have a look at the braking and acceleration loads. Generally, axle is the biggest component of that along the length of the skid, but making sure that equipment is bolted down sufficiently and supports are sufficient to restrain all the piping and tanks and anything else that may be on the skid. Or if that's not feasible, we'll have notes that's putting that on the shipper to make sure any smaller items or actuators or small bore piping as required is temporarily strapped down, restrained for transport. And then we have seismic loading and design. This is kind of like transport actually, where we're designing for the structure being the structural effects of what it's sitting on, loading the structure. So in the case of transportation, it's a truck bed or a train car. In the case of seismic, it's the ground itself moving. So the further you get to the coast, the more of an issue this is, but for heavy structures, it can be an issue even here. So most of our stuff, we're doing conventional seismic design. We're just making sure that everything's strong enough to resist a seismic event or earthquake. Just between the anchor bolts and the structure and the bracing, or something like this, this tower here, the structure itself and the connections to the foundation, it can just shake and not fail and not yield anywhere. As you get into more kind of higher seismic areas, more complicated structures, may get into where you're actually designing parts of the structure to fail in a seismic event. So you have ductile connections between structure. Essentially, if the ground moves, those connections will plastically deform and absorb energy, but they're designed so that the structure will not collapse when that happens. But if we ever see the big earthquake out on the coast, there's definitely going to be a lot of building remediation needing to be done. Hopefully everything stays standing, but to go in and repair those connections and review and do repairs to the building before it cannot be occupied again. Smaller event or out in the lower seismic areas we've designed so it's fully intact. And then the other option, I'm not going to try this video, but it's an interesting one if you want to have a look on your own. But for higher seismic areas or specialized structures, the other option is to isolate the ground from the structure. So have like a bearing, have the whole structure sitting on like polymer flexible bearings so that when the ground shakes, it's isolated from the structure and the structure will stay put and the ground will shake below it. Not something we get into too often, but it's an interesting solution if you look up seismic isolation bearings. Apologies. And then, yeah, looking at our engineering calculations and the software we use. So to look at all that loading and design our structures, we generally use S-frame and S-steel as our kind of primary steel analysis packages. There's a few out there in the wild, different companies. This is kind of a more complex design where we're actually using plate elements to look at a shell or support off a pile here. But we'd often be using, we're also using Dyna when we need to for dynamic foundation design and Excel and pen and paper or maybe or a computer pen these days. But hand calcs and diagrams are definitely still a part of it. And while this looks interesting to do it, out of plate elements and meshed here, we're often just using a more simplified approach. What we have here is the stick frame, S-frame model of a piece of a pipe rack that's braced in the horizontal and braced in the vertical. And piping loads are being applied to it in the software, and this green is showing the deflected shape. It's emphasized. The actual deflection values are printed here, so like 20 millimeters, not a meter, whatever this appears to be, but that's just for visual. So we can look at exactly how much this is deflecting, how it's behaving under load, and then how much loading is in the individual members. We can see the shear loading, the bending moment loading. And then we can get into the actual steel design in this package as well. We'll always be checking this, but we have all the structural steel in there accurately and the loads accurate. In this case, we actually, sorry, let's flip back for a second. We actually have the piles modeled. These are steel piles modeled as well, using springs based on the soil properties. So we can actually approximate how much the foundations are deflecting as well as the structure above. Get accurate loading, and then we can look at it in the S-steel package or similar packages that will actually give us a utilization ratio of each and every steel member in these structures. So if these turn red, that's bad. That means that with all safety factors included, we're over 100% of the strength of the beam or column or whatever the steel member may be. So we definitely don't want that, but that's the visual we can get, and we'll go through and remembers their statics and dynamics. We can do hand checks as well, just to verify that what we're seeing in the software is real, and maybe just do this on its own if we're just doing a smaller project or a small addition or a single beam. Have a look at the actual formulas for what the axial and bending forces are. Confirm that. And then, yeah, we have a frame, often do. We're dealing with frames, so might load in the middle. That's what it'll look like. You have bending of the connections you have to deal with. and bending in the members. Resolve that into internal forces. If we're looking, well, for steel beams, it's relatively simple, but when you get in composite beams, we have to look at this a little more closely to see if there's going to be failure at any attachment points. And then we have to look at, for columns especially, it kind of goes back to those diagrams of failure at the beginning, but often the material won't actually fail. You know, we're dealing with structural steel most of the time. Can often have 350 MPa actual failure strength. That's newtons per millimeter squared, which is very strong. So like the actual crushing capacity of a short steel column is very high. But as you get into a slender column supporting a pipe rack, supporting a building, anything like that, it's going to be governed by buckling. So long before it reaches the yield strength, we're going to see the geometry control it, and it will buckle and fail. So, and kind of back to some statics here, but Euler buckling is what we're looking at. So depending on the how the column is restrained at the top and bottom is how we is what informs the design. So the lower this number, the better. The stronger the column. On the worst case, it's restrained against rotation, fixed at the bottom, but fully free at the top to move. That in effect doubles the length of the column for your analysis. So for L is 2L, but if you have restraint at the top and bottom, you actually reduce the effective length up to 0.5 of the height, and then the in-between options are where you're, if it's pinned, just restrained against axial and lateral forces, but not rotation, and you'll get a full, just use 1x the length for buckling, and then an in-between scenario here. But very often governs our structures, and we need to make sure that it's not deflecting too much, and then this eccentric load becomes an issue and causes progressive failure. That needs to be reviewed, especially for heavy loading and tall, flexible structures. And then we get into the steel design itself. For beam, again, this kind of goes back to my original my failures, but same thing. For a short laterally supported or laterally supported beam, it will fail when it actually reaches the yield strength of the material. But for long, slender sections, something like this at the top, or this one here, it'll end up governed by buckling, lateral torsional buckling. So even though you only have vertical load on it, any sort of small eccentricity or small lateral force, or just it will cause the beam to want to try and buckle sideways, the top flange to move, and it can fail like this long before you reach the actual strength of the member. So we have to make sure it's either laterally restrained or sufficient strength and stiffness to resist it over the length if it's unsupported. Similarly, that's a pretty common one. Maybe anyone who does kind of pipe rack piping design, I expect there's a few of you, but you see a lot of times where this is a pretty common scenario. Pile sticking out of the ground, W section, which is Y flange section, an I-beam sitting on top. I-beams can fail if you add enough load to the top. That web can buckle, like you see here, but often that takes quite a lot of load. That comes into play in things like bridge girders or really tall, slender I-beam sections. But very often comes into play when we have piping sitting on the beam, because the expansion and contraction of the piping itself will laterally deflect the top flange, and that can be enough load to cripple that web. So often we'll add these. We try and do it only where needed, because every time you add a plate stiffener, it's bunch more welding, but it greatly increases the strength of your support for lateral loads, lateral piping loads. So when it's needed, it gets added, and that will fully restrain this this web from buckling under lateral loads. Oh, yeah, and then this is maybe the most important thing we do, to be honest, and something that's kind of looked over. If everything's welded together, fully welded to each other, the connections are generally not going to be the governing part of the structure, but very often they are, because we need to, for site assembly, we might have issues where we can't do hot work. So we want bolted connections. If it's in an operating plant, where we can get the beams in and have everything kind of flown in by crane and bolted in place. Then we're designing bolted connections, and those need to be reviewed fairly closely to make sure we don't fail at the connection. So different types here, pretty common shear connection, just a couple bolts through the web of a beam, or we'll have an end plate moment connection that's fully rigid if needed. Something like this with an I-beam with an end plate bolted to another I-beam column. And we have to look at all the failure modes. So bolts can tear out, they can split, they can fail the overall cross section, they can fail the holes and bearing. It's also an issue for lifting lugs, so we have to look at all these cases. Welded connections as well. Have to look at the strength of the weld itself. Make sure you're not failing either the weld or the material on either end of the connection. And then you do get into local buckling issues as well, where there can be enough force from the bending on a connection like this that you could buckle the web of the column. So we may need to add stiffeners like this. These are the same stiffeners I was talking about for pipe supports, where you just add a stiffener plate. Or if the web itself fails, you need to add a doubler plate, just another extra plate thickness in this connection on the web. So we'll get into that. And then you can also get amplification of the loads depending on the geometry from prying action. So something like this situation where you're pulling with the bolts inset, you'll actually get a higher bolt load than RU, even though your load is 2 RU because of this prying action. So I have to look at that as well. And yeah, connections, very important. I would say that's probably the most common place for a structure to fail. Yeah, just quickly, we also do concrete design, lots of structural steel, but if we need to, and for foundations especially, we'll get into reinforced concrete design. Very similar design process, except that it's a composite beam, so that there's reinforcing steel inside of it as well as the concrete section. Can either fail by crushing the concrete at the top or yielding the steel and tension at the bottom. So we're looking at both of those cases and designing accordingly. Yeah, I think I'm getting near the end here, but the serviceability, talked about that. We're looking at how a structure deflects. We have to make sure it doesn't deflect so far that the piping is impacted, but we also have to make sure that other aspects aren't impacted. So things like a bridge crane in a building have very specific deflection requirements of how far that building can deflect under wind or other loading, so that crane can still operate, still roll where it needs to, and not hang up or get stuck because the track's too deflected. Also, not too much, but in our purview, but for commercial structural design, you're looking at story drift and how much the building can actually move. Like a high-rise building under wind load before it starts cracking finishes or cracking windows or cracking building panels, and just for the comfort of the occupants itself. If it becomes too much, you're gonna get nauseous up there. So the steel code has requirements outlining kind of for different types of structures what those requirements are. We can link to those. And yeah, and then when we get down to the ground level, we're designing foundations to support all this. So left, we've got a pile design, deep foundation. You'll see them for bridges, lots for pipe supports. We're driving in a steel pile, say 8 meters below grade, hammer, it's just a weight driving it in. That pile needs to go deep enough that the combination of the friction on the shaft of it and the bearing at the bottom of it is enough to resist whatever is sitting on it. And then for shallow foundations, and just a big concrete block sitting on the ground, just looking at the bearing capacity. So what kPa or what pressure it's putting on the soil, and if that's above or below the maximum allowable bearing capacity of the soil that our geotechnical engineer has sorted out. For deep foundations, we also get a little bit of feedback on the energy used to install it. So it's not perfect, but various formulas and more in-depth pile driving analysis where you can attempt to back calculate the pile capacity based on how much energy was used to drive it in and how far it moved. So the weight of the hammer, how far the hammer's dropping before it hits the pile head, and then how many blows it takes to move the pile into the ground, either 250 or 300 millimeters generally. So if we don't have good geotechnical information, we'll be conservative and rely on the driving energy. If we do have good geotechnical information, we'll still have a look at that as kind of a second check. Make sure the soil's looking how it's supposed to. And then the other big issue for foundations is frost depth, especially in our part of the world here. So footings, basements, kind of standard residential foundation, or it's just block of concrete sitting on the ground. Those have to be down below the frost depth. Depends on where you are in the world. It can be 4 to, well, it can be less than 4. Around here it's 4 feet at least, up to 8 feet. So we head further north, and for structures that are isolated that don't from any sort of heated building. So you're digging down and just setting that bottom of that footing below where the seasonal frost can get to, worst case. And then for piles, you're driving that pile past the frost depth, and the frost can actually grip the side of the pile and try and pull it out of the ground. Call that ad freeze. So we need to make sure the pile is deep enough that the grip of the non-frozen soil below is enough to hold it in the ground, which means that lots of light structures, small pipe supports, electrical supports, anything like that, if it is sensitive to frost movements, we're going to be designing the piles to a minimum depth, kind of no matter what. So even though we end up designing for the frost pullout, not for the capacity of the vertical capacity of what's sitting on it. Yeah, just quickly, if we need to, we get into dynamic analysis where we're looking at the dynamic behavior of the foundation, making sure that it's adequately restrained and not getting into where we have resonance and excessive vibrations from the equipment that's sitting on it. Yeah, and I think probably last but not least is get into soil retaining structures, or for structures anyway. Few options there, and depending who we're working with and what height of wall and what the soil conditions, we might lean on the geotechnical engineer, do a type of wall like you'll see for a bridge abutment where those concrete panels are just the facing, and it's the actual soil with mesh and soil anchors inside of it that's using the soil itself as the retaining structure, called mechanically stabilized earth wall. Or on the structural side, we can look at just designing a simple concrete wall, or sheet piling, pretty common. We've been down on the riverbed here in Calgary. They're doing this everywhere as a flood wall where similar to driven piles, but instead of a pipe pile or an H pile, you're driving in these corrugated sections. Can be quite an efficient retaining structure or flood wall, as long as you don't have utilities below. And the soil is appropriate for being able to drive those in. And some sketches we'll do to get information to our design team, produce eventual drawings, some types of support structures. Oh yeah, I'll talk about this quickly. See if I can leave 5 minutes at the end here. Just the importance of construction loads. Sometimes that does need to be left to the contractor where they need to brace and temporarily support stuff, but we also need to be aware of it. We might have a piping assembly like this where the supports are all good once everything's bolted up because the piping itself is very stiff. But if they happen to set a bunch of the piping on the support first, we also need to make sure that support's okay. Had a failure here, where either we needed to make it clear that we need temporary support during construction, or we need to brace and make sure that support's adequate for the construction load. So usually do the latter if we can, just less problems. And harping on again, but the importance of support stiffness. We can't always just go off whatever structure is nearby and support the piping load. That's kind of an example. If you have a piece of pipe with a heavy valve in the middle, each end of the pipe sitting directly on a post or pile, the middle's cantilevered over. That support may be so flexible, depending on the size and stiffness of this pipe, that it literally isn't doing anything. So we do, right back to the beginning here, that's the importance I see in interfacing with our pipe stress group and making sure that they're aware of the stiffnesses of the supports, and we're actually providing a support that's both strong enough and stiff enough to support the piping adequately. Yeah, the non-structural part, this is a bit of grading. Won't get too far into it, but we do it too, where we can use that survey data to work with our civil designers to do civil 3D model, provide sections, what needs to be cut, what needs to be filled, provide quantities for pricing and for scheduling, how much earth needs to be moved, how much material needs to be imported, if any reinforcement is required. And get into kind of both for site grading and backfill and compaction and support of piping as well. So with that, about 5 minutes left, but open it up here if there are any questions. Happy to flip back.
Sorry, go ahead.
I see a hand up. I'm not hearing.
Go ahead, Alan.
Okay, good. Thank you. Appreciate all the information. That's really great. Do you have any experience with helical piles? These are like a 9-inch pipe with flutes at the bottom of them. Do those work well?
Yeah, they can. I think I had one here somewhere. See if I can find it. Yeah, I mean, yeah, right here. Yeah, I didn't really cover that. I mean, same sort of design constraints. Yeah, they can work very well under a few situations. The pile itself will be more expensive. Have to fabricate the helixes rather than just a straight piece of pipe or a straight W section or I beam to drive into the ground. But yeah, they do have several advantages. These will be drilled into the ground. And that can mean that depending on the size of pile and how much torque is required to get into the ground, you could use something like a skid steer at the end of an excavator with a motor on it. So definitely a great option if you need to reach over equipment and get piles installed. Also less vibration. We have clients that require them if we're installing new piles next to existing operating equipment. You're not hammering away on the ground and vibrating everything around there. They're also removable. So if we do temporary installs, we also use them. Yeah, and I guess the disadvantages are, cost, needs a fabricated pile, and then certain ground conditions, they just don't work. Large cobbles, they have large, like geotech says, there's like large kind of rocks in the soil. It's gonna be really, really tough to get into, get these drilled in. So depends on the soil conditions, but yeah, they can definitely be a good solution. Similar design, it's a combination of the bearing on the helixes. So force up on these helixes and then friction on the shaft of the pile as well. And we're going to make sure it's in deep enough that these helixes are held down below frost depth. But yeah, we have used them quite a lot. Not often we design them in-house. We'll work with like a piling company that kind of has standard designs, and we'll provide the loading requirements and then review them, but that seems to work well.
Thank you. Appreciate it.
Yeah, no problem. I just got another question here for pipe rack with multiple support types. How do you determine the optimal support arrangement to control pipe movements while minimizing structural steel tonnage and support reactions? I mean, I guess it's an iterative process with our stress group. They're going to tell us if they need the piping to be anchored or restrained. We're going to work with them to hopefully put it at an efficient location. If we're just talking a pipe run across a site, we'll try and put, say, have a, I don't know, 150 meters of piping. We'll try and anchor it near the middle so it can expand and contract without putting a lot of load on the structure. But that's not always possible because sometimes it does need to be anchored near to the connection points. So we'll have to work with stress if that anchor needs to be near a nozzle to keep the nozzle loads on a tank or pumped down. We just may need to design a stiff enough structure to make that happen. So if we really need to, we can get into like concrete thrust blocks, but usually we'll do our best to do it with braced steel structure. That's the most efficient. Yeah, kind of the more area we can take up to kind of make a larger footprint with a larger brace structure can help keep that light, but still stiff enough for those loads. So yeah, kind of a back and forth, but those are kind of the main items.
Okay, 1 o'clock, so I guess we'll have to wrap up. Thanks everybody for joining us and participating today. If you requested a CPD certificate, we'll email that to you, and we'll also post the webinar on YouTube on the Landmark channel. Any other specific questions, please contact myself or Chris. We are going to take a break over the summer on our technical series and be picking this back up in the fall. So thanks again, and have a great day.
So everybody.